In section 5.2 part 1, you will evaluate polynomial functions. In these three examples, we're going to decide whether the function is a polynomial function. If so, we're going to write it in standard form and state its degree and leading coefficient. This first function, f, is not a polynomial function, so we'll write no because of that negative exponent. All exponents on our variables have to be whole numbers. G of x in example 2 is a polynomial function, but it's not written in standard form, so we'll rearrange or commute the terms to get it in standard form. The term of highest degree goes first, and that would be x to the fourth. The exponent on our variable determines the degree of the term. So our next term in standard form is negative 0.8 x cubed. That term is of the third degree. And last is negative 5. That constant term, negative 5, is of degree 0, because if there were a variable there with an exponent, that exponent would be 0. Anything to 0 power is 1, and 1 times negative 5 is negative 5. So that's why we have no variable multiplied to our constant, negative 5. Now this polynomial is of degree 4, and the leading coefficient, and I'll just abbreviate, the leading coefficient is the number multiplied to the variable with the largest exponent. So our leading coefficient is 1. H of x is also a polynomial function, and we'll put it in standard form. Term of highest degree is negative 8x to the fifth. That term is of the fifth degree. And next term is positive 1x to the fourth. That term is of the fourth degree. Then we have negative 4/5 x squared. That term is of the second degree. And then we have our constant term at the end, the square root of 10, which is of degree 0. Okay, then we'll pick out the degree, which is 5, largest exponent of any term, and the leading coefficient is negative 8. Okay, here we have a table of common polynomial functions. We have our constant function of degree 0. We have our linear function of degree 1. We have our quadratic function of degree 2, cubic function degree 3, and quartic function degree 4. In these two examples, we're going to state the polynomial function's degree, type, and leading coefficient. So in this first example, the degree of g of x is 4. The type is quartic because it is of degree 4. It makes it a quartic. It's a quartic polynomial function with two terms. Okay, and then the leading coefficient is 8. Okay, in h of x, we have a degree of 3. We have a type, because of degree 3, the type is cubic. It's a cubic trinomial because there's 3 terms to this polynomial function. And the leading coefficient is negative 1. Here we're going to use direct substitution to evaluate the polynomial function for the given value of x. So we're going to evaluate this function f when x is equal to 2. So we're finding f of 2, or y, when x equals 2. So all we have to do is substitute in 2 for x wherever we find x in our polynomial function. And then simplify. So negative 2 cubed is 8, or 2 cubed is 8. 2 squared is 4. Negative 12 times 2 is negative 24. And we have negative 5 at the end. So negative 3 times 8 is negative 24. Plus 4 minus 24 minus 5. So usually when I evaluate or simplify, I add my negatives together, so I'm going to get a total of negative 24, negative 48, plus negative 5, negative 53, plus 4. So I'm getting a value for this function when x is 2 of negative 49. Okay, let's try that again with h of x. In for x, we're going to put negative 5. So we'll substitute. And we'll simplify. Negative 5 to the 4th power is going to be 625. And negative 4/5 times negative 5 squared, that's 25. So we have 625. In this product, 5's will cancel, top and bottom. So we're left with negative 4 times 5, or negative 20, plus 7. And again, I'm going to add my positives and negatives separately and then add the two together. So I'll have my positives first. 625 plus 7 is 632. And if I subtract 20, the value of this function when x is negative 5 is 612. We have another method for evaluating polynomial functions, and that method is the synthetic substitution. We're going to use synthetic substitution to evaluate the polynomial function for the given value of x. So to use synthetic substitution, we're going to put that x value 2 through the coefficients of this polynomial, and the coefficients are negative 3, 1, negative 12, and negative 5. Every degree has to be represented, and this polynomial is of degree 3, so 3, 2, 1, 0. I have every degree represented 3 through 0 with coefficients. So to synthetic divide, I'm going to put down a 0 in this first column, and I'm going to add to get negative 3. Then I'm going to multiply. 2 times negative 3 is negative 6, so I'll put that right here. And then I'm going to add this column. 1 and negative 6 is negative 5. And I'll multiply again. 2 times negative 5 is negative 10. Now I want to add this column, which is going to be a total of negatives, negative 22, and I'll multiply one more time. 2 times negative 22 is negative 44. And when I add this column, I get a remainder of negative 49. This remainder, with synthetic division, is the value of the function when x is 2. So f of 2 is equal to negative 49 by synthetic substitution. Okay, let's try that again on h of x. We're going to evaluate h of x when x is negative 5. So we'll put that negative 5 through the coefficients 1, negative 1, negative 8. And now you can see I don't have an x term in my polynomial function, which means that coefficient is 0 and negative 1. Remember, every degree has to be represented, and this is a quartic of the 4th degree, so I want to make sure 4, 3, 2, 1, 0. Every degree is represented from 4 to 0 with coefficients. So now I'm ready to synthetically divide. I'll put a 0 in this column, and I'll add. 1 plus 0 is 1. I'll multiply. Negative 5 times 1 is negative 5, and I'll put that here. Then I'll add this column to get a total of negative 6. I'll multiply negative 5 times negative 6 is 30, and I'll add to get 22 and multiply. Negative 5 times 22 is negative 110. I'll add this column and I'll multiply. Negative 5 times negative 110 is positive 550. And when I add to get my remainder, I find that it's 549. So the value of this function when x is negative 5 is equal to 549. Now, whether we use direct substitution or synthetic substitution, we will get that value for this function. Include with your notes of this video guided practice problems 1 through 7 found on pages 338 and 339 of your textbook.